Okay, so I want to find the internal normal shear moment at D. Okay, uh, and there you go. So this is a compound beam. Okay, what I'm going to do is I'm going to draw my free body diagram. Okay, with that, I'm going to recognize that I don't have any horizontal components, so the AX is going to be 0. Okay, what I'll do is I'll start over on the right side, and I'm just going to recognize from symmetry. Okay, if this is 10, each one of these has to be 5. Okay, from symmetry, which means over here, this guy has to be 5 as well. I'm going to replace that, um, uh, excuse me, that distributed load by a point load acting right at the center, and it's going to be 6, right? Which is the area of, 3 times 2, okay? Which means that over here, if I've got 6 going, no, I've got 6 and 5 going down. That means I have 11 going back up over here, okay? And then I think I'll sum my moments, right? And I'm going to assume that moment's in this direction. We'll find out. So I'll sum my moments about A. I'm going to have my moment. Okay, 11 goes to 0, but then I'm going to have negative 1.5 times 6 and negative 3 times 5. Set that equal to 0. That moment then becomes, this is the moment at A, I should say. Maybe I'll put that in there like that. That moment at A becomes 24. Okay, so those are my reactions right there. Now, what I'm trying to do here, and I probably actually didn't need that 24 because I'm going to make my cut right here, right? So what I'll do is I'm going to draw the right side of that beam right there, and I'm going to do it just like this, okay? Because I'm going to redraw my distributed load, which is going to have a magnitude of 2, okay? Uh, Over here, I'm going to have my 5 acting straight down as well. And then at D, I'm going to have N, I'm going to have V, and I'm going to have M, like so. Again, don't worry about what directions you draw it in there, as long as you know when you get the result what direction it's ultimately in. You can make any assumptions, up, down, left, right, clockwise, counterclockwise is fine. Okay, I need to redraw the distributed load as a single point load. This one is going to have a magnitude of 3 right at the center there. Okay, and then from this, I can sum the forces in the x direction. Only thing I've got is negative n, so that's got to equal 0. Okay, and then I've got my sum of the forces in the y direction. So I've got v, I've got minus 3, and I've got minus 5 equals 0. So from that, I learned that the shear force, I have it drawn correctly, and it's 8 kilonewtons. So again, my assumption that it was up is correct. Okay, and then I'm going to sum the moments, and I'll sum the moments at where I cut it, which of course is point D. Okay, I need to include my bending moment, that's the negative m. V and n both go to 0, but then I have negative, now instead of 1.5, this distance right here is just 0.75. So it's going to be negative because it's half of the 1.5. So that's 0.75 times 3. And then negative the whole thing times 5 equals 0. From that, I get m equals negative 9.75. All that negative sign means is I drew it as a clockwise moment. It's actually a counterclockwise. Not a big deal as long as you understand what direction it's going in. You draw it in whatever direction you want. It's fine with me. Okay. So again, when you do this, you find those reaction forces, right? Once you have those, then you can make your cut, draw one half of the body that you're looking at, remembering to redraw the distributed load and recalculate, point load for that newly sectioned distributed load, and go ahead and find your normal shear bending moment as shown there.